Number 42. A beryllium-7 atom, which has a mass of 7.0169 AMUs, decays into a lithium-7 atom, which has a mass of 7.0160 AMUs by electron capture. How much energy in millions of electron volts, which is capital M EV, is produced by this reaction? Okay. All right, so it seems like they're giving us information for a balanced equation. So let's first write out that balanced nuclear equation. Now, in this case, it's beautiful because they give us both the mass number, which are the top numbers, and the bottom numbers, which are the atomic numbers. Now, we're starting off with beryllium, so we got Be. It's got a mass number of 7, so that's protons and neutrons, and we got a atomic number of 4. Let's just pull these in a little bit. And it says it decays into, so I know that I'm going to yield my beryllium into my lithium, so Li, 7,3. And they did tell me that we have a electron capture reaction going on here. So if you are capturing a subatomic particle, in this case it's an electron, that electron is going to be caught and it's going to be in your reactants. So just know the wording here, because electron capture means that your electron is going to be on the left side. If it said electron emission, that means that your electron is going to be on your product side. So in this case, we're going to add on the reactant side. We're capturing, we're keeping it for ourselves, that electron. Now, it doesn't really matter whether you put an E value here for electron, or electrons are also known as beta particles. So you could put a B here, doesn't really matter. Maybe we'll keep it with the electron and we'll put an E here. And just know that electrons are not in the nucleus, right, of an atom. So it has a mass number of 0, and the charge of an electron is always a -1 charge. And here now, 7 plus 0 is a 7, so that checks out. And then 4 plus a -1, or 4 minus 1, is a 3. So we know that we balanced this equation perfectly. Okay, so here is our balanced equation. Now, they did say that we're starting off with a mass of that beryllium of 7.0169 AMUs, and the lithium atom is 7.0160 AMUs. But now, the idea here is that, well, you know, you're capturing an electron as well. So if that's the case, this electron's got to have some mass. So that's where your knowledge of a mass of a single electron comes into play. So the constant value here is anytime that you're talking about an electron, the general mass is going to be 0.00055 AMUs. So let's write that out for this guy. So it's a little bit negligible because it's really, really small, but still, we should use it for this equation. Okay, so we got the beryllium, whoop. We got the electron, whoop. And we have the lithium, whoop. Okay, now, at the end of the day, though, we want to find out how much energy is produced by this nuclear equation. So if we're solving for energy, we're looking for capital E. But now I say to myself, well, what formulas do I know that have to do with energy in my nuclear chemistry chapter, right? And there's only one. It's probably the most famous equation in all the land. Nobody really uses it, right? Not for chemistry, maybe in physics. But generally, you've probably heard of this equation. It is, boom, E equals mc squared. The capital E is the energy that we want to solve for. So we're looking for this capital E, which means that we should know the M and the C. Now the C is a constant value. This is the speed of light. So speed of light, and the correct units for speed of light in this formula is 3. Now you could use 2.998. Maybe I'll use that to just be a little bit more specific, but you could say it's 3, right? 2.998 times 10 to the 8th meters per second. Now the M is not the total mass, right? M definitely stands for mass, but in general, it's called a mass defect. Now, in this case, defect is talking about the difference. Basically, what this formula is talking about not in an ideal world, but in an actual world, there is never going to be conservation of mass. So what Einstein brought up, and that's whose formula this is, Mr. Albert Einstein's, right? Albert Einstein said that the difference, the leftover mass gets converted into energy. So we have to find out how much energy was lost during this process. Okay, because we don't want the total amount. We want to know how much didn't get converted. Well, let's see. Now we have these two values. If I add these two values together, 7.0169 plus 0.111.00055, you get roughly 7.01745 total AMUs. But now we see a little discrepancy here, because if it was a theoretical, perfect world, which anything in life is never perfect, life lesson, right? We're not perfect, and that's totally fine. That's what makes us beautiful. But, obviously in chemistry as well, right? We started off with this amount of mass, but now on the right side of the equation, it's not conservation of mass because we're not having the same amount. So we have to find that difference, right? We have to find the mass that was converted into energy. So if I just take that value and I subtract it by 7.0160 AMUs, I'm going to find the difference. I'm going to take this value and subtract it from 7.016. Okay, 0.00145 AMU, and that was the difference, or that is the defect. This is now the mass that actually got converted into energy. And that's what we got to find out. So now we know that our M value is 0.00145 AMUs. However, when we do this problem, we can't be having AMUs. For this formula to work, this has to be in kilograms. So kg. Christina Glazer. Whoo, that's me. Anyway. So, I do have a conversion down here to go from AMUs to grams. Now, if you do want to use your dimensional analysis, you most certainly can, right? We just got to take this value, and if we're solving for grams, grams are going to be in the numerator, so you would multiply this value. So just to kind of show you, 0.00145 AMU. We don't want AMU anymore, so that unit goes on the bottom. We want grams. So the 1.6605 times 10 to the negative 24th goes on the top, and the 1 AMU goes on the bottom. And now you have grams. So I'm going to take this value and times it by 1.6605 times 10 to the negative 24th. And I get 2.4077 times 10 to the negative 27th grams. But now we can just convert to kilograms, right? Grams to kilograms is always dividing by 1,000. So I could take this value and just divide it by 1,000. Okay, so now we have 2.4077 times 10 to the negative 30th. So we can just, maybe, let me grab this a little bit, bring this over here. I'm just going to get rid of this information. So you can pause the video if you need to write it down, but it's got to go. We used this already, so I'm just going to get rid of it. Whoop. And let's now bring this down, I guess, a little bit. We'll keep bringing this down. We also use this value, so we don't really need that either. So now we have a little bit more room. Okay, so E equals M c squared. The m is going to be the 2.4077 times 10 to the negative 30th. And then we have the speed of light, the constant value, 2.998 times 10 to the 8th meters per second. We could plug this all into the calci at once. So E equals, we'll take this whole number, times it by 2.998 times 10 to the 8th, times 10 to the 8th, and then we will raise that value, we'll square it, and I'm just making sure that I'm plugging in everything correctly. There we go. Press enter. 2.164 times 10 to the negative 13th, and just know that this is in joules. So when you're using this formula, you need kilograms because we're in physics world basically here. So the standard unit in physics for mass is kilogram, not grams, which is the standard one for all your chemistry equations. And then joules is going to come out of it. But now the last thing we just need to do is just basically convert it into millions of electron volts, million or mega, it's the same thing. And I have that conversion down here. So if we want to, times by a ratio. We don't want joules anymore, so joules goes on the bottom. We want millions of electron volts, so MeV. 1 million electron volt equals 1.602 times 10 to the negative 13th. This goes bye-bye. And now, this divided by 1.602 times 10 to the negative 13th divided by that. Okay. So we get 1.35, and that's million electron volts. And that is the final answer. What'd you think? I hope this helped. Let me know in the comments. Thank you so much for viewing the video. Subscribe to the channel, and I look forward to helping you in more questions. Thank you so much for coming here for all of your educational needs. We got physics, we got math videos on the channel. My brother and I, we love to help you guys out. We got over 5,000 videos out there for you guys. So thank you so much for making this channel what it is. It wouldn't be like this without you guys. So you guys rock. Keep studying hard. I'm always going to believe in you. Good luck on your tests and quizzes, and I'll talk to you soon. Okay, bye-bye.